So today we're going to be looking at movement of charges in an electric field, how the charges actually move. So this is really almost a summary of almost everything you've learned in physics up to now.
Oh, crap.
Almost. Okay? So if you've sort of been snoozing for a month, this will be a good review. So pay particular close attention today. So you'll recall from your research that Millikan had the charges suspended between the electric plates. He filled with the voltage until he got the charges exactly balanced and they were suspended, right? Which meant that the forces were balanced. And I had you draw this little picture showing that the electric force was exactly equal to the weight force. Remember that?
Yeah.
No, I didn't say yes, I remember that. No.
Actually,
Excellent. Now, Devin has been pestering me, wondering, Mr. Bennett, what would happen if the electric force wasn't balanced by the weight force? What if one was bigger than the other?
Let's go up.
Or down, depending on which one. Exactly. Very good. Okay. It is equivalent to the idea of, you remember when we had like blocks on somewhat level surfaces? Let me just try to redraw that again. Blocks on surfaces here, right? And you might have like an applied force like this, and then you'd have like a small friction force resulting in a net force, right? Right? Because when they're balanced like this, what's the net force, Riley? Zero. Okay? When they're not balanced, then there is a net force, and when there's a net force, how does that mean there has to be a word starting with A? Another word starting with A? Acceleration. Acceleration. So that is sort of the topic of the day. Okay? So that's what I'm saying here. If the forces are not balanced, there will be a net force on the charge causing the acceleration. So in this case here, I've got my electric force up. As you can see, it's the smaller one. And so my overall net force is going to be down. And it's going to fall. In fact, it's going to fall. It's not going to accelerate at the standard 9.8 meters per second squared. It's going to fall at a smaller acceleration. It'd be like dropping a ball on the moon kind of thing. Right? Because there's a force upward. So using this net force and acceleration, we can solve problems for motions in the electric field. This is exactly like the unit on dynamics that we did earlier. Okay? So basically what we're doing is we're taking all those sideways force applied, force friction questions and sort of just turning them 90 degrees and letting things fall as they may. Let the chips fall as they may. All right. Now, first of all, let's just see which way these forces are, because if they're not balanced, what's going on? First, consider a line of charge and a single point charge placed nearby. And I wouldn't worry too much about copying this down. What I'm saying here is if I've got a plate, right, a positive charge here, and I've got a small positive charge right there, right? Well, this guy here pushes that way, but this guy pushes that way, and this guy pushes that way, and this guy pushes that way, and this guy pushes that way. What happens to the horizontal components? Like what happens to the one that's pushing this way and the one that's pushing this way? Well, they're going to cancel out, and the whole net force is going to be in which direction? Straight down. This is my net force. In other words, don't worry that there's some pushing from the side, because there's just as many guys pushing from the other side. Okay? That's what I'm saying. Because you don't need to worry about that. Was anyone worried?
Yeah.
Were you? Yeah, you were.
I'm still worried.
Yeah?
I don't know.
Okay. Now, if the plates are oppositely charged, then this effect is enhanced. The field is constant and directed away from the positive to the negative plate. Now, the edges of the field do bulge a little bit, right? Because there's no charge on the outside that sort of balances that off. So we're going to assume that all of our movement is occurring nice in the middle there, right? We're not going to worry about ones that are sort of like out here on the edge that are sort of going like that. That's a little bit too advanced for us. So don't worry about that either. In other words, assume that the field is completely uniform. What do I mean by that? Straight. Same everywhere. Absolutely, yeah. Okay. So that's what I've got here. For simplicity's sake, we will assume that the field between the plates is constant throughout. And I think we're ready for some sample questions. Yes, we are. Just let me find them. All right, now as per usual, I'll be starting with a little simpler one and moving our way up here on the degree of difficulty scale. You have this problem in front of you, so you just need to copy down the answer. So I have a 1.0 times 10 to the minus 4 kilogram charge, a 3.2 times 10 to the minus 19 coulombs is dropped in electric field. The plates are 1.5 centimeters apart, and the electric field strength is 1 times 10 to the 15, and it all sounds very confusing, doesn't it?
Yeah. No, that's, yeah.
Determine the net force on the object. So what am I being asked? What's the net force? What are the actual forces on the object? Well, as always, we have a electric force up and a weight force down. And I guess before I can find the net force, I need to do what? Well, I got to find the electric force and I got to find the weight force. The weight force is always easy to find, isn't it? Right? Do I have the mass? I have the mass. What's this one here? 3.2 times 10 to the minus 19. Q. No, in Q, that's charge. The plates are 1.5 centimeters apart. That would be a D. Have we even looked at D on any of these? The electric field strength is 1 times 10 to the minus 15. That's my E. Okay, can I get my weight force? Yes, I can. Weight force equals mass times gravity. So 1.0 times 10 to the minus 4 times 9.8. Actually, pull this. Oh, I got a calculator right here. 1 exponent minus 4 times 9.8. 0.00, this one didn't give it to me in scientific notation, 9.8. Or 9.8 times 10 to the minus 3, I guess, right? I probably should have been able to do that in my head. Minus 4, right? Right, gotcha. Minus 4. Gotcha. Okay, what about my FE? I've got E equals F over Q. The E is 1.0 times 10 to the 15. The F is what we're solving for. And the Q is 3.2 times 10 to the minus 19. Yeah, 15 right here. Now, would you expect the exponents, like the times 10 to the minus 4, would you expect the FE to be the same times 10 to the power of? You would expect it to be in the same ballpark of strength, right? Okay, so 1 exponent 15 times 3.2 exponent minus 19, and I get 3.2 times 10 to the minus 1, 2, 3, 4. Excellent. All right, so Devin's got it all figured out. He knows that the weight force is, in fact, which way? Down. So should we put a negative sign there?
Yeah.
We probably should. We probably should have had negative on our 9.8.
Oh, it's all right, though.
This one's positive. So in other words, my net force is, right? It's my electric force plus my weight force. 3.2 times 10 to the minus 4
Oh, I didn't write anything down.
minus 9.8 times 10 to the minus 4. You're just enjoying the show, Mike?
I was trying to follow along.
That's okay.
Wasn't minus.
Now, why is it minus 9.8? Right, because it's going down, right? I'm adding them together. I'm finding the net force. So I get a net force of minus 6.6 times 10 to the minus 4. Dude, good for you.
Thank you. The second part is obviously times 10.
Shut up. The first part's obviously minus 6 points.
No, that's not that hard, is it? Like, really, the only thing that makes it hard is that times 10 to the power of nonsense, right? Really.
3.2. Can you move your recording?
Yep.
Thank you.
Okay, so I'm hoping that you found the weight force first. Mass times gravity. 4.5 times 10 to the minus 6
Wait,
times
what is this?
9.8. 1.5. Oops. Minus 6. 8.
So he's at your house right now.
Yeah, I left a note on him.
No,
Just a sticky.
You know, I put him in Brother Kitty's cage with some food
4.41 times 10 to the minus 5.
and water. No, that's what I got.
Like taped piece of paper.
Now, how many people have figured out that when I go E equals F over Q, that should be an F. Anybody figured out that that means that F equals QE?
Yeah.
Yeah? Anybody started to write that on their own?
No.
You can go ahead and do that because we're going to be solving for F here.
I usually just wait and then I figure it out.
Yeah, I understand, but once you realize that it's always going to be the same and we're going to be solving for F an awful lot, you can simply go 9.2 times 10 to the minus 15. The E strength is
What is E?
3 point. It's the same thing, yeah.
So why can we
You
just do it?
do it, yeah, by all means.
Okay,
Knock
do
yourself
it
out.
the same way.
It's to the plus 9. Though.
Do it out
Be careful.
Whatever charges your electric field, man.
Be careful.
Whatever around you.
On the electric force.
Oh, there's a lot of ice.
No, that's what they do. You have to ask for like no ice.
I don't know.
2.944 times 10 to the minus 5.
Yep, that's right.
Okay. And of course, the weight force is negative. So my net force is going to be
That.
2.944 times 10 to the minus 5. Subtract 4.41 times 10 to the minus 5.
This is the same thing as we did last
Yeah, it's exactly the same thing.
But it's just the scientific notation.
Yeah. So I get a net force of minus 1.466 times 10 to the minus 5. Okay, so those are the same 3 steps that we did before, but now I need to find the acceleration. How am I going to find acceleration? Here's where I'm going to take F net is equal to MA.
Mass acceleration.
Mass. Oh, yeah. Now, what do I know? I know my net force here, right? So minus 1.466 times 10 to the minus 5. The mass was 4.5 times 10 to the minus 6. Like, really, it's just being careful with scientific notation, really, isn't it?
It's not that hard.
No, it's not.
Formulas.
Solve for A by dividing. I get an acceleration of minus 3.26. Now, does that seem reasonable?
Yes, it does.
Why does that seem reasonable, Chris?
I don't know. It just seems like a reasonable
So,
number. It's not too
what's the
big. It's not too
units?
small.
That's in meters per second squared. Like, how come this one doesn't have scientific notation?
Because acceleration.
Well, here's the question. What would it be if there was only weight force on it? What would the acceleration be?
We zoom it.
Be fast.
Minus 9.8, would it not?
Oh yeah.
Gravity.
Oh, that's fast.
Right? So, can it be anywhere close to 0? Well, 0 would just be stop. So it's got to be some number between
That is
0 and 9.8. So that's a perfectly reasonable number.
Sounds good.
Perfectly reasonable. Okay, so now how the heck do I do the next part where it says,
And next
how fast is it traveling after 1.5 seconds? This is way back to kinematics.
Oh man.
This is where we're going to go something like A equals delta V over delta T. This is that review that I was talking about. See, I don't need to review at the end. I do it as I go.
Are we gonna review at the end?
No.
Oh my god.
Minus 3.26 is my acceleration.
We're not gonna review at the end.
Yeah, it's in your course outline from the first day.
But we're not gonna review the whole year.
No.
You've been all year.
Just taking stuff and building on
Yeah.
Yeah.
So now I'm going to solve for my delta V. My time is 1.5. Easy now, Chris.
Shoot, sorry. Oh,
Multiply,
shoot.
yeah, okay. Don't make it worse. Times by 1.5, and I get my delta V is minus 4.89 meters per second. And because I started from rest,
West 4.9.
4.89, because I started from rest, right? Since the initial velocity is 0, 3 dots mean therefore my final velocity is also minus 4.89.
Yeah.
Right?
Is that it?
No, it's not, because there's even one more part. It says, how far will it have fallen? How far will it have fallen?
What
Oh,
does it say? Sine?
V equals
Since
D over
since
T.
VI equals 0.
V equals T over T, man. We could do that instead of that.
All right.
video project.
Okay, now,
Thinking out loud.
how far will it have fallen? As Chris has aptly pointed out and got us on a really weird path. V bar equals D over T, man. But do I have V bar?
A lot. No, you gotta find
I
out.
do not. Before I can do that, I'm going to have to go V bar equals VI plus VF over 2. You'll remember, Riley, this from way back when, this review that I'm doing now. What is the initial velocity?
0.
0. The final velocity we've determined to be minus 4.89. Divide that by, basically divide it by 2,
Pretty much.
right? Basically divide it by 2.
2, negative 2
So divide that by 2.
times.
So minus 2.44. And now I take that and plug it in there, right? See, if you're getting this stuff, you don't have to review because you learned it back then.
Yeah.
Minus 2.44 is my V bar. Solve for, we're trying to find the distance. Do we remember what the time was?
1.5.
1.5 seconds. Excellent. 1.5 D equals times 1.5. Minus 3.67 meters. Wow, that was a lot of work.
Mr. Bennett, I'm sorry, but that's a really bad five.
Where? Oh, looks like one point C.
Perfect.
How many marks would that whole thing be worth, do you think?
Probably about 6.
1 there. 2.
3.66.
3.
Probably 3, maybe 4 for this. 5,
6.
6, 7, 8. Something like 8 marks. Basically, am I not right? That is almost all the formula manipulation of the entire course, all rolled into one big giant question. That is pretty cool.
And I actually get it.
And if you get it, then you should be good.
Why didn't I get it earlier?
I don't know.
To get it now.
I don't know. Now, clearly, we do not have time for number 3.
Clearly.
Clearly, we do not, right? So I guess we have a couple options here.
We do
I could challenge you to do that on your own and then check to see how it goes. Or I could just do it on Tuesday.
We should do it. Oh, yeah. Oh, it's the weekend tomorrow. I keep thinking it's like Tuesday.
You know what? Here's what we'll do because we got a second or two. Can we just, before you pack up, don't pack up, don't pack up, don't pack up.
I'm just going to put it in my ring.
Just don't, because I want to read it.
I'm going to read it anyways.
Millikan observed a droplet of unknown charge accelerating at minus 2.3. So he got the acceleration. He determined the mass to be 5.3. He knew the electric field strength. He was asked to find what charge is on the droplet. Is that not basically exactly what Millikan just did? He figured out the acceleration and then worked his way back to the charge, right? This question here, I gave you the charge, right? And then you got the acceleration. So this one, I'm going to work the other way. Okay? So we will, I'm sure you won't be able to sleep all weekend
Oh, for sure.
without knowing the answer.
I'll be stressing about that.
But I will enlighten you on Tuesday.
Definitely thought it was Tuesday today.